Swayam Prabha. Digital India. Educated India.
Welcome students. So this is the week 10 lecture number 1. Here we are going to study about the topic that is mentioned in this slide. This is about viscous fluid flow. Actually we have gone through this topic before, but in a much more crude manner. The main objective of this module is going to be able to derive Navier-Stokes equation from scratch. So, how to start from the beginning and derive the Navier-Stokes equation, and we are expecting to dedicate around depends, but at least 3 to 4 lectures in this module. And a difference from the regular classes to this one is going to be that I will be teaching it by hand. We will take the help of slides as little as possible, because Navier-Stokes equation is something that needs to be done by hand, and in the derivation using the slide it has been found out is not helpful that much for this particular thing. So, we will go very slow in this, and we will complete this module in, let us say, 3 to 4. So, okay, so now I will minimize this and use this board now. So, this is, the topic is viscous fluid flow. So, I will be speaking too, because I think my writing might not be that much helpful to you. So, so to start with this one, some general points. One is a fluid is a substance that deforms continuously under the action of a shear force. Okay. This means it cannot resist shear. All right. A solid, however, can resist shear and remain at rest. All right. In fluid mechanics, a matter is classified into fluids and non-fluids. So in thermodynamics, the normal definition is classification in solids, liquids and gases, but in fluid mechanics it's fluids which consist of gases and liquids and non-fluids. Non-fluids are mostly the solids. Okay. So another basic revision is properties of fluid. So first is kinematic property, that is velocity, acceleration, vorticity, rate of strain, angular velocity, etc. So there are many other properties like this kinematic. Transport properties, are viscosity, thermal conductivity, mass diffusivity, thermodynamic properties like density, pressure, temperature, entropy, enthalpy, etc. So we will go to another page, and there are some other miscellaneous properties. Miscellaneous properties includes surface tension. It's important to know these properties, at least know what those are. Vapor pressure. See, whatever properties I have just mentioned, if you know what those are, your knowledge of fluid mechanics is complete. Okay. Eddy diffusion coefficient. All right. So apart from that, so these are some of the properties. So now we go into little bit more detail in kinematic properties. So the idea of this particular lecture today is that we are going to write what actually material derivatives are, and we see the rotation, how the fluid particle gets rotated, and try to obtain the strain rates and those quantities. That is the main objective of today's lecture. So first thing is substantial derivative / material derivative. So we are just going to mention what that is. Okay. So if we say let q, x, y, z, comma t is any fluid property, and V bar is equal to u x y z comma t I cap plus v x y z t j cap plus w x y z t k cap denote the velocity field. So, if we assume q is any property, any fluid property, and v given as u I cap plus v j cap w k cap denotes the velocity field, then total derivative of q, that is d capital Q. So, dq will be given as del q del x into dx plus del q by del y into dy plus del q del z into dz plus del q del t into dt. Okay. Hence, time rate of change of the property q is given by dq by dt is equal to, so del q del x is there, and this dx by dt, this becomes dx by dt into dy by dt plus del q by del z into dz by dt plus del q del t into dt by dt. All right. So, what we have done is we have divided this by dt. So, we are going to the next page. So, finally, we can write dq dt is given by, because dx dt becomes u del q del x plus v del q del y plus w del q del z plus del q del t. All right. So, this dq dt is called substantial derivative. Okay. Usually written as dq dt. All right. These three are convective derivative. All right. And this is local derivative. So, this is substantial or material derivative, this is convective derivative, and this is the local derivative. All right. So, starting with a new, so if there is a fluid element, can undergo the following 4 types of motion or deformation. What are those? Of course, it can do translation. Translation is moving from one point to the other. It can do rotation. It can do extensional strain or also dilation and shear strain. All right. So, we are going to derive something which, so we are going to derive the strain rates. So, one thing I would like to take your attention to is this figure. Okay. So, we consider a fluid element ABCD. So, we consider this element A, B, C, D, okay, and that moves in an XY plane. The position of this element at times t, this is position at time t, and its position at time t plus dt is shown like this. Okay. So, now with reference to the above figure, we can observe the following transformations. I mean of transformation or deformation in the fluid element within the time interval of t plus dt. See, we can see that B has translated from B to B dash. Okay. We can also see that this diagonal BD has rotated anti-clockwise to B dash D dash. You see that? And we can also see the dilation or the extensional strain of the element. Because of rotation, you know, these elements, some of these will dilate and some of them will elongate. Okay. So, now using this figure, we are going to write down. So, we will keep this handy, okay, and start deriving. Okay. So, we can see from the figure that I showed you, we can say tan d alpha is equal to del v del x into dx dt divided by dx plus del u del x dx dt. Okay. So, let me go back to this figure and try to explain you some of these components here. You see, so this was length dx, right. When it goes there, you know, if we consider in time dt and with the velocity u, so this entire length will become dx plus, so change of velocity in x direction, if it is del u del x, correct. If it is del u del x, then the total change, this length is going to be del u del x into dx into, you know, dt. All right. So, this is the total distance that this is going to be there. All right. And the translation that this will have, this one is going to be only, see, this was at origin, I mean this was at 0 before, correct. So, it will be del v del y. Okay. So, it would have also, it has traversed over a length x, so dx into dt. All right. Similarly, from here to here, you see dy, it was already at y. So this length is dy plus the rate of change of v in y direction. So del v del y into dy dt. All right. Similarly, this will be only del u del y into dy dt. I hope you have understood. So there are angles d alpha and d beta which we are going to calculate. So the translation, because it is u dt, you see this translation from this point to this point in time dt is considered to be u dt. All right. And this one, it has a velocity u in this direction, and this one, this fluid particle has a velocity v in this direction. So this has translated to all right, u dt and v dt if it was 0 0 here. So this is done using geometry only. Okay. So a fluid particle having velocity u and v respectively in x and y direction translates, they rotate also, you know, because of the shear. So this particular figure we are going to see, we are going to derive some important results about it. Okay. So tan d alpha, you see, okay, I am not going to open it all the time. So I will show you here. So this is d alpha here. So this is d alpha and this is d beta. All right. So tan d alpha was del v del x into dx dt divided, just simple geometry. And what is going to be tan beta? Tan d beta is going to be del u by del y into dy dt divided by dy plus del v by del y into dy dt. Okay, simple trigonometric rule. So for infinitesimally small time interval dt, if the time interval is very small, that is dt, we can obtain tan d alpha is d alpha. Okay, is limit dt goes to 0 tan inverse of del v by del x into dx dt divided by dx plus del u del x into dx dt. Okay. All right. This implies d alpha is limit dt goes to 0 tan inverse so we divide by dx, so this will be del v del x into dt divided by 1 plus del u del x dt. All right, we just cancelled dx from up and down. Okay. And in this case, what is going to happen is, because dt is small, this is going to be 1 plus this is going to be 1, and it will be del v by del x, because this will be approximately equal to 1 del v dt. All right. So similarly, the way we obtained d alpha, d beta is also going to be del u del y into dt. This is another important results, del u and del beta. So now the rotation of the element is given by the arithmetic mean of the angular velocities of sides BC and BA. Further, the rotations d alpha and d beta are in opposite sense. Hence, the rate of rotation in the z direction considering the anti-clockwise rotation as positive is given by, so rate of rotation in the z direction is given by d in z direction is given by, simple, right? So the rotation of the element is given by the arithmetic mean of the angular velocities of side BC and BA, which is half d alpha dt minus d beta dt. Here we have assumed that the anti-clockwise rotation is positive. So because d alpha by dt and d beta by dt we have found out from the previous, you see d beta. So if you see using this one, for example, d beta by dt can be written as del u by del y, all right. So we can simply write del alpha by del t is del v by del x, and this will be del u by del y, okay. So similarly, for x and y directions, simply we write sigma x by dt is equal to half, okay. So we have found out for z, same way we can find out for del w by del x, del w by del y minus del v by del z, and so d sigma y by dt is half del u by del z minus del w by del x. So let's call this equation number 3, okay, and the other two equations, you know. So let's say this is 1, and this was equation number 2. All right. So, equations 1 to 3 can be actually written in vector form as, because there are 3 components, we can simply write is equal to half. All right. So, so I would like to close the lecture at this point, and we will resume from this particular page in our next one. Thank you so much. See you in the next lecture.